I'm starting with the great name of Allah, who is most beneficent and merciful. Today we are going to discuss our final year project, and the name is Design and Fabrication of Combined Savonius Darrius Wind Turbine. I myself, Muhammad Umair Rafiq, with my group mate Midat Fatma, and we have done this project with the kind supervision of Engineer Shakil Ahmad Jiskani and with the keen supervision of co-supervision of Engineer Ghulam Akbar. So I would like to call Midat Fatma to start a formal presentation.
So these are the contents of our presentation that will be described in this presentation later. So let me start the brief introduction of our project, that what is our project about. So basically we are working on two different kind of turbines. Both the turbines are vertical axis wind turbine. One of them is Savonius wind turbine, which is the simplest wind turbine, and it takes wind from all direction, and it's a drag type wind turbine. So that is the reason that whatever the wind's direction is, it's gonna move, and it has a high starting torque but less efficiency. So the efficiency of Savonius wind turbine is around 17% to 17%. The other turbine on which we are working is the Darrius wind turbine. This turbine has a low starting torque but better efficiency as compared to Savonius wind turbine. So its efficiency is around 40%, and it can easily integrate into buildings, and it has two further types: egg shaped and egg beater and egg shaped. So now let me tell you that what we are going to do in our project. So we are going to combine both these turbines, Savonius and wind turbine. So basically we're going to take the advantages from both the turbines, and the overall efficiency will be improved. Also, it will be self-starting because the starting torque is provided by Savonius wind turbine. So we don't need any extra motor to start our turbine, and it will be able to work on low wind speeds. Yes. So this is the problem statement, that what was the problem in previous designs of turbines. As you know that there are a lot of different designs of turbines, but the problem with other turbines like horizontal axis wind turbine, they are quite big in size and they create huge noise. So they cannot be placed in domestic areas. Also, they cannot take wind from every direction. They need particular direction of wind so that they can start working. And also we know that Savonius and Darrius separately have disadvantages, like Savonius has less efficiency and Darrius has less starting torque. So the motivation for this project. So what was our motivation? As you know that there are a lot of regions in Pakistan that do not have proper electricity, but they have proper wind flow. And even if they have low wind energy throughout the air, throughout the year, so we can install our project over there. We can have turbine over there because our turbine is able to work on low wind speeds. Also, its size will be smaller, its cost will be less, and it will be more efficient. So it will be able to be applied in domestic areas and commercial as well. So basically the aim of this project is to improve the disadvantages of Savonius wind turbine and Darrius wind turbine. So this is a literature review from which we have taken help to design our project. If you see the first paper here, so it says that the ellipse type blades are more efficient. There are two types of blades, ellipse and the classical one. So we have used ellipse type blades because they have better power coefficients. And also we have taken a number of blades from literature review. We know that two blades of Savonius wind turbines are better than three or more than that. And in this paper, we can see that the torque and the angle of rotation of Savonius wind turbine. So basically this is the overall literature review that we have done to make our design more efficient and better. So this is some some recommendations for Darrius wind turbine and also the combined wind turbine. So we can see that the wind tunnel, which is used in most of the literature review, is a subsonic wind tunnel that we already have in our university. So we have used a subsonic wind tunnel, and also these are the steps that we have followed to design Darrius wind turbine. And also, as I have already mentioned, that our design will be able to work on low wind speed. So the low wind speed on which others have tested their wind turbine was 3 meters per second. And we have also used minimum wind speed 3 meters per second.
So now let's come towards the aims and objectives. These are the following steps that we have processed through get our achieve the desired product. So first one is a literature review, wind resource assessment, design and servers, fabrication, and then testing. So we have followed these steps to get our product. So first of all, our first step was wind resource assessment, because we have done this for our project, where we have to install our project. If we are installing our project at Sakhar, so we have to analyze the data of Sakhar, that how wind flows in that area. So that's why we get the data from the NASA. Okay, so we get data of 5 years, previous 5 years, and we analyze looking at these drops, that we can see that the average wind speed is 3 meters per second and 5 meters per second throughout these 5 years at 10-meter height. So we get the data from the NASA, because we have to install this project at some place, at some specific place. So we have to analyze the behavior of wind at that place. So we get the data at 3 meters per second and 8.7 meters per second from that graph at 10-meter height. This data is shown at NASA and at 10-meter height. So we have analyzed that data and came to conclusion that we should analyze on 2 wind speeds at 3 meters per second to 8.75 meters per second. So we get the average wind speed 3 meters per second, 5 meters per second, and we have done some calculations on these 2 average wind speeds and calculate the power. So here's the calculations. So we assume the CP value is 0.4. This is the power of coefficient, and our density is 1.225 kilogram per meter cube. Density of air, this is the density. These are the constant parameters that we are assuming. So we get a total power of 16.64 watt or 17 watt because this is our prototype. So that's why we are not getting so much power. So according to these parameters, we have fixed that we can see that the diameter of rotor, and these are the formulas and Savonius calculation and Darrius calculations. We have made it in tabular form to analyze that how we fix our parameters for this turbine. So this is the radius of the rotor that R is d/2, and Savonius calculation 0.145. We have selected the parameters according to the prototype. So how much power we can get from assuming these parameters. So our Darrius radius was 0.25, and total area of these 2 turbines is 0.218 meter square and 0.3 meter square of Darrius turbine. So our theoretical power at 3 meters per second, as I have told earlier, that we have analyzed the data. We analyze data, and then we get 2 wind speeds, wind velocities, 3 meters per second and 5 meters per second. So that's why our 3 meters per second is a low wind speed, because these turbines work on at low wind speed. So that's why we have made calculations at 3 meters per second and 5 meters per second. Our project is unique because of low wind speed, because this worked perfectly at low wind speed, 3 meters per second, 5 meters per second, up to 8 meters per second, as we have analyzed the data previously by NASA. So this is the power calculations, that where the CP is involved, it means we have some losses, because we are assuming the losses CP value 0.4. Here we can see that. So after calculations, after getting the values, after putting the values, then we get the power is about 0.8057 watt, and Darrius power was 1.9845. So our theoretical power at 5 meters per second. Now we can see that as wind speed increases, then power is also increases. So 3.73 watt we are getting from Savonius, and 1.18 watt we are getting from the Darrius. So this is the velocity at 10 meter height. At 10 meter height, we are getting the highest speed of velocity we are using in our calculation at 5 meter per second for both the turbines. So power in air. So this is the power without losses, that how much power air possesses. So it is understood that it is obvious that in ideal case we can get the power from air fully, but in actual cases there are some losses. That's why we are not getting so much power from the air. We are extracting less power, and we can analyze that how much power air have at this wind speed. So this is the calculations for the wind speed, that how much power air has and how much we can extract from that air. So that was a 2 watt, and actual power in air was 4.96 watt. So we can analyze here from this table that actual power was 2 watt. The power in wind was 2 watt, but there are some losses, so that's why we are getting 0.805 watt at the end at the power. So at Darrius calculations, we can see that it was 4.96 watt. So with losses, there was some losses, so that's why we are getting 1.89845 watt. So this is the huge difference. That's why, because air is not completely converted into energy. We are not completely converted our energy to from 4.96 to 1.998. This is the huge loss. So power for double stage and H-shaped rotor, as we can see in our design, that we have designed double stage rotor. So that's why our power would be double. So that's why 3.73 was our Savonius power. Here we can see that at 5 meter per second, we had 3.73 watt. So it was double stage. So that's why we are multiplying this power, so getting 7.46 watt throughout. So Darrius gives a 9.18 watt and Savonius gives 7.46 watt. So total it was 17 watt we are getting from the two turbines. This is the gearbox calculations. The gearbox is very beneficial to increase the speed, to increase the RPM. So as we know that it depends on our generator, that how much it required RPM. So that's why if generator needs high RPM, so we need a gearbox. If we are getting 300 RPM, so the generator needs 3000, then we must convert using the gearbox to achieve desired results. So that's why we have some calculations that how much power we are getting from the shaft of the turbine and how much we needed to run the generator. So that's why this is the power, this is the actual speed WS, and by WE, WS shows that the output power, and W is the input power, how much the turbine rotates, how much speed it has, and ZE, what is ZE and what is ZS? ZE is the number of teeth of driving gear by the number of teeth of the driven gear. It means ZE shows that in our project, ZE is the teeth of the bigger gear, and ZS is the teeth of lower gear. So that's why if we are calculating by using this, that we have 300 revolution per minute at the turbine shaft. So we need 1881 RPM to get the desired results. So we put that data in that value in that equation. So we are getting 6.27 ratio. So we need 6.27 ratio to get 1881 RPM for the generator to run, to get the desired output. So we used to increase the speed at output side. So we select the teeth of gear in such a way that the ratio would be 6.27. So we can see that our ZE is 69 teeth and ZS is equal to 11 teeth. So we are getting 6.27. So it means that if we are using 69 teeth at bigger gear and we are using the 11 teeth at lower gear, so we get the 1881 revolution per minute to generate electricity at this RPM. So these are the results. These are our results of power calculations in a tabular form, that at 3 meter per second we are getting power from Savonius 2 watt and Darrius 4.96 watt at 3 meter per second. and theoretical power was 0.8 and 1.98 watt. This was a power at power in air, and this is the power at output side. So at 5 meter per second, we are getting 9.32 watt, and from the Savonius, this is the power in air, and at Darrius 22.96, it was the power in air. So we are getting 9.18 and 3.73 at 5 meter per second. This is the theoretical power. So these are some designs that and some parameters that we have assumed from our prototype. This is the output diameter of our turbine, of our Savonius turbine, 0.305 meter or 305 millimeter, and this is the parameter in inches. This is the input diameter where the blade is placed. This is the height of our turbine. This is the total height, 16.5 inches, and this is the rotor. This is the radius. Sorry, this is the radius of our Savonius turbine. That it's about 2 inches. So this is the dimension of Darrius turbine. This is the Darrius turbine. As you can see that this is the height is about 600 millimeter, diameter is about 500 millimeter, chord length is 120 millimeter, and area is about 0.3 meter square. These are some parameters for designing of this turbine. We have designed this turbine on SolidWorks, and this is the fabrications. This is the next step. After the design of these turbines, then we do fabrications. After designing on SolidWorks, we have fabricated these blades of this turbine. Material used for fabrication, there are different material we can use for our turbines, but we have some limitations for our project. So that's why we have used iron copper. This is not so much expensive, so we have used this iron copper. So it is required that our material should be economical and it has good tensile strength. So we prefer iron copper. It was not so expensive, so that we use iron copper. This is some steps. These are some steps. Fabrication of single stage Savonius turbine. First, we have done the single stage Savonius turbine fabrication, and secondly, we fabricate the double stage Savonius turbine, and the third one we designed the Darrius turbine. We fabricated the Darrius turbine at the last. So these are some fabrications. Double stage Savonius fabricated the design model, and the Darrius blade is a fabricated model, and this is the assembly of both Savonius and Darrius. So combined Savonius and Darrius turbine we can see here. So in this assembling of both turbines, so this is our actual product. So we assemble both the turbines and with proper angle iron frame, and this is the generator which is coupled at the shaft of the turbine. So both the fabricated turbines are assembled now. The Savonius turbine inside and the Darrius turbine outside of Savonius. One has a good self-starting torque because one has good efficiency of self-starting, and other one has a good torque. So it compelled Darrius to move due to its high starting torque. So these are some requirements. These are some problems which were overcome by assembling of both the turbines. Once Darrius starts to rotate, we will get some momentum and continues to rotate easily with better efficiency and low wind speed, as we can analyze by our results. Wind tunnel testing, this is the next step. So we have tested our project on wind tunnel, subsonic wind tunnel at 2 wind speed, 3 meter per second to 8.5 meter per second. These were some speed ranges that we vary the speeds about 3 meter per second to 8.5 meter per second. So first at 4.6 meter per second, our turbine starts rotating. At 5.2 meter per second, we are getting 388 RPM at the turbine shaft. So at 7 meter per second, we increase the speed further by wind tunnel by varying it, and we are getting 500 RPM. And at 7.5 meter per second, we are getting 600 RPM. And at 8 meter per second, we are getting 7.750 and 8.5, 800 RPM. So these are the RPM when generator is not connected, when there is no load connected at the shaft of the turbine. So these are the no load RPM. So these are no load RPM we are getting from the both the turbines. So this is ANSYS Fluent, which was done by my groupmate. So she will further elaborate.
So we have also simulated our result on ANSYS software, which is a software that is used to analyze electrical related machineries, and it can also predict lifetime of different type of machineries. So it can also used for automobile engineering and electronics engineering. There are different steps of ANSYS Fluent that we have to go through. First is a geometry in which we can make our design. Then it's a mesh where ANSYS software itself divide your geometry into different steps. Then we have to do the setup, like we have to give wind velocities, pressure, and everything. Then it's the solution. Then the software itself calculates all those values and then it gives the results. So now we have analyzed both the turbines separately. So what we have done is that, as you can see, that this software is able to tell you the flow and how the wind is flowing and also its impact on our turbine. So from here you can see that that wind is entering in our mesh box, as you can see. So from here the wind enters, and from this part the wind is exits. Okay, so here we have Savonius wind turbine. After attacking this turbine, what we get from the wind velocity, here are some of the results. Like you can see the area of inlet, outlet, force of how much force is coming towards the turbine, and what we get after it leaves the turbine. Then we have torque, mass flow of pressure, and then sum of pressures. Same steps were done for the Darrius wind turbine. Here again we can see that wind is entering from this direction and it leaves our turbine from this direction. So again, same calculation was done for this turbine. Area, force, torque, mass, flow of pressure, and sum of pressures were calculated.
So now let's come towards the hardware results and discussion that we are taking from our project. By varying the wind speed of tunnel, there comes up the different voltages at generator terminals. So as we can see that if you are changing the speed of wind tunnel, so we are getting the different results at the turbines shaft. So we are getting 195 revolution per minute at 4.3 meter per second when the generator is connected. So we have assumed some parameters that we are given 4.5 ampere of excitation current and 20 volt of voltages to our generator. For these results, we get the result at 300 rpm and generated voltage were 4.2 volts. Now by using gearbox, when rpm is increased, then voltage is increased by 25.2 volts. So after assembling, after fixing the gearbox, our voltage would improve, as we can discuss after discussing this result. So at 4.3 meter per second, we can see that we are getting 2.7 volts and 195 revolution per minute at the shaft of turbine. And at 6.3 meter per second, as we increase our speed further, so we are getting 3.2 volts. So these are the voltages which are now better than the previous one. So we are getting 228 revolution per minute now. So at this revolution per minute, we are getting 3.2 volts. So we increase our speed further by 7.5 meter per second. Now we are getting 279 revolution per minute at 4.28 volts. We are getting now 279 RPM at turbines of turbine shaft, and now at generator side, generator terminals, we are getting 4.28 volts. So now let's come toward the conclusion. The goal of this project is to design and fabricate combined Savonius and Darrius wind turbine on software and hardware. So that was our goal, that we will first design, then fabricate it, and then we analyze data at ANSYS Fluent software. So we achieve our goal. So that was our main objective. The software used for this project was SolidWorks and ANSYS Fluent. So we use these both softwares as well, and we get the desired results, and we can see here as we have showed our result previously. For hardware testing, we use a subsonic wind tunnel, as I have discussed earlier, that we are changing the speed and getting the desired RPMs and voltages as well. So we conclude our result that at 4.3 meter per second, we are getting 195 revolution per minute and getting 2.7 volts without the gearbox. So at 7.5 meter per second, we are getting 279 revolution per minute. At shaft turbines of rotating shaft can produce 4.28 volts. So at 7.5 meter per second, it was our objective to run our turbine at low wind speed So these are two wind velocities through which we analyze our results. So 7.5, we are getting 279 revolution per minute, and at these revolution per minute, our generator rotates and gets 4.28 volts, as we have seen here. From ANSYS flow, we get the 8952.19 Pascal pressure at inlet. So this is a very good pressure at inlet side, and outlet pressure was 1989.53 for Darrius turbine. So this is good for good result. And for Savonius turbine, the inlet pressure is 30892.3 Pascal, and outlet pressure was 1875 Pascal. The inlet force for Darrius was 1966.25, and outlet force was minus 1903.9 Newton. For Savonius, inlet force was 6.77692 exponential minus 7, and outlet was minus 0.388642 Newton. This project can also be used at highway. So what was the application? How, where we can use this project? So we can use at highways, we can use at off-grid applications and we can use it at hybrid application, as a hybrid application where we are using solar. So when we are using street lights in daily life, so solar lights are getting charged by the solar panel. So if we are using the hybrid model by this wind and solar combined, so when the sunlight is not here, so if wind is good, so by using wind speed, so we are getting good quality of power, and we can store, and then we can run our system as well. So also this can be used for off-grid and domestic applications. We can also use for one home and not for multiple homes. So these are some recommendations in future work. Following recommendations can be considered for future work. If the size of turbine is increased, the output can be increased to generate more RPM. As we told earlier that we have just made a prototype. So that's why we are not getting huge power. So the next one is that the gearbox can be used to increase RPM at minimum wind velocity. So we can increase the RPM by using gearbox. So we get we can get the desired results. It is also suggested that the low RPM permanent magnet generator can be used to generate more electrical power. So as we showed earlier that we have used a high RPM generator, so we are not getting good voltages. So if we use the low RPM generator, so we get the maximum voltages, because it gets low RPM to generate a maximum power, maximum voltages. Thank you.